हाँ. Good morning, everyone.
तो ये मैं अपने सिस्टम से अभी ऑन करके फिर ये कर दूँगी.
Right.
सर ऑडियो सॉरी वीडियो ऑन है.
Hello. Can you see or hear me?
Yes.
Yes, sir.
I can see you.
Sorry for this weird camera angle. I'm taking this lecture from a classroom where the camera setup is different and it's set up for a classroom environment, not for this online class. Just give me a few seconds. Okay. So I'm going to keep my camera off throughout this course because there's no point seeing the top of my head. Is that okay with all of you?
Yes, sir.
Okay. Could you guys mute yourself when you're not discussing anything with me? Okay. Is this presentation visible to all of you? Could you just give me a confirmation?
Yes, sir.
It's visible.
Yes, it is visible.
Yes, sir.
Okay, excellent. So let's start. First of all, welcome to this course. It's a course on MOS Device Physics. Let me first, so all of us ran here to start the class on time and everything. So I'll just take a quick breather and let's start with some info. Okay, I am Avirup Dasgupta. I am an assistant professor here at IIT Roorkee, and I also work as a developer for the BSIM group and the Berkeley Device Modeling Center. So I work on all the industry standard compact models that are used for various circuit design and various applications in the industry. My area of research is primarily semiconductor devices and compact modeling. Apart from me, Professor Anand Bolusu will also be taking a part of this course. He's a professor here and he used to work earlier in Freescale Semiconductor till around 2008. He works primarily on circuit performance model and design, device circuit co-design and all of that. And we will have a few guest lectures from Dr. Kanan N from Cadence. So these three people are going to be your instructors for this course. Let me get some input from you. What are your thoughts or expectations when you think of this course, when you think of the name MOS Device Physics? Do you have any prior experience in this? Have you done a course related to this in your undergrad? Do you work on a related field in the industry? Could you give me just some idea of where you stand? Anyone?
As a basic understanding, the basic functionality of MOS and little bit of a small signal model, I understand. Otherwise,
Just a minute.
um,
Uh, just a minute. Okay. Sorry, I didn't hear the person who just spoke. Could you just repeat? I'm so sorry.
Yes, sir. So basic of device, MOS device, and I mean the functionality, those complete basic structure I understand, and little bit of small signal modeling also.
Okay, excellent. Anyone else? Anyone else with a background in MOS device physics or has a slight understanding of these devices?
It is not very useful for us in the industry, but it's good. Having this knowledge is very important, and we learned basic things and some of the issues which are the lower nodes facing these days. So these basic things we have some ideas, nothing more.
Excellent. No, I understand that your work will not directly involve working on devices, but yeah, as you pointed out, it's good to know
Yes,
the
yes.
building block, right? Yeah. Okay.
Also the you can add MOS capacitances, uh, you know, on different saturation, linear region or cutoff region, things like that. Uh, I hope they involve MOS physics, MOS device physics. So yeah.
Okay. 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 Yeah. Yeah. They do. Yeah. Okay. Let's see. I'll go back to the presentation now. Okay. So let's look at the course structure for this. This is what we are going to be talking about. I will start with a introduction or a recap sort of a thing where we go through some basics of semiconductor physics. This will be a very small, short intro, so I won't go into the depth of it. Maybe 3 to 5 hours of discussion on this, depending on how much you already know. If you know this a lot, then I'll skip this quickly. That's the starting point. And the other things are, after this, we are going to talk about two terminal devices. So primarily diodes and MOSFETs. I'll be focusing on MOSFET more. Diodes will use primarily to understand the various parasitic diodes that are already there in MOSFETs and MOSFETs. And next is the main topic of MOSFETs, which are your industry workhorses. And we then go into some of the more significant effects of the modern generation, which are the short channel effects, and then we'll go into small signal and large signal models, some structural effects, noise, and at the end we have two classes dedicated to catch you up to what is happening in this field of MOS device physics and how it impacts you. So one is this discussion on circuit simulation and the models that are being used for it. These models actually dictate all of your simulation output and stuff. So whatever is the physics going behind that, we need to have some idea of it. And the last topic is about the advanced devices. As someone just pointed out, there are a lot of problems. I wouldn't say problems, but new physics coming up in the modern devices as we are keeping on scaling these devices. So we'll discuss some of them and some of the modern devices. Regarding this course, there will be some assignments given from time to time. This is the weightage that I think would best suit this class, where you guys might not be free every time, so it's better to have it more or less equally distributed. So I'm keeping this weightage. If any of you wants to come up with a better solution or a suggestion, you're always free to, and you can tell me. So we'll have assignments, we'll have a midterm exam and an end term exam. Is this okay with all of you?
What is term, professor? Term paper?
Term paper is something, it's sort of like writing a report. So I would also this course is, as someone pointed out, is slightly away from what you do in your regular industrial work, but say this has a very direct effect on what you do in your regular industrial work. So I was thinking that maybe by the end of the course, towards the end of the course, if you could all think of and maybe submit a report on how this is actually impacting your day-to-day work, or even if there is an impact, even if you think that there's no impact, it's fine. I just want to know your thoughts. So I was thinking of asking you to submit a report on that. That would also help me evaluate where you stand with respect to this course, where your understanding is, and there will be some grades associated with that. But this is not finalized yet, so I will decide this as the course progresses. You will get a better idea of the course. I will get a better idea of what you people are thinking of, and then we can decide on this at the end of the course, whether we want to do this or not. Okay.
So one question. So
Yeah, sure.
the last point what you said, right? So when the modern devices, so will it be including only FinFET or multi-gate device or a very brief of multi-gate devices?
Sorry, your voice is not clear. Could you repeat, please? Sorry.
So the last point, advanced nanoscale FETs. So would it
Mhm.
include only FinFET, multi-gate device or very brief of those two?
So the advanced nanoscale devices, my plan is to give you a flavor of all of the devices that are coming up. So one is FinFETs. So because this course talks about MOS device physics, right? So it's not very specific to bulk MOSFET or SOI or FinFET or anything. It talks about the physics of these devices. Although primarily in all of our examples, we'll be mostly relying on bulk planar devices. But this thing applies for all MOS devices. So in the advanced nanoscale FETs part, I'm going to talk a little bit about FinFETs, about SOI devices, about the upcoming stacked nanosheets or ribbon FETs or multi-bridge channel FETs. So different companies call it by different names. Basically, these are gate-all-around devices. I'm going to talk about that. And then I'm also going to talk about some of the devices that are in research, but probably not in the production level at industries like negative capacitance and ferroelectric FETs and all of those upcoming sort of areas. So we won't go too much into the details of or the physical equations and everything of these devices, like the ones that are in research, but we'll just tell you what's happening, why people are looking at them, if there is a chance of them appearing in the future and stuff like that. So you're up to date on whatever is the state of the art. Does that answer your question?
Yeah, okay, thank you.
Okay, so that's the exams part. I would like to start with some context. Don't worry about this. This is just so that we are all on the same page. I'm sure most of you already know this. So as you can see on the slide, there have been quite a lot of milestone events in the MOS device development. And the reason we are studying these devices is because they are sort of the, the building blocks of the modern semiconductor circuits and ICs. So I am not sure if you already know this. There was this guy called Lilienfeld in 1926, 1928, in these 2 years, and I think also in a later year, he submitted 3 patents. This guy was an academic professor, and this guy submitted 3 patents for what we now know as, MOS device. And in a way, this is the first MOS device or a MOS transistor. Well, it wasn't literally the MOS device we know or the bulk planar device that we know. It was the first sort of a semiconductor transistor that was, shown. At the same time, there was another guy, I forget his name, who submitted a patent in around 1928 or 30, which was sort of similar, and also Bell Labs was working on it, obviously. However, when you go to Google and search for, the MOS device, whatever, the first transistor and everything, you would probably get the name of Shockley from Bell Labs and everyone, but that their work far precedes Bell Labs' work. Bell Labs' work was slightly different and more improved. It was slightly derived from Lilienfeld's work, and they were working on these devices using germanium primarily at that time. In 1945, during the World War and everything, they were trying to develop these devices for military use, where they would be more reliable than vacuum tubes. And this study of semiconductor devices led to a new sort of field of physics opening up regarding surface conduction and surface states and everything. So Bardeen and Brittain were working on this. And in 1947, they first showed the surface inversion insulated gate field effect transistor, which is basically an insulated gate FET, or a metal insulator semiconductor FET, sort of. There was a interesting, competition or fight that was happening at that time between Bell Labs and Texas Instruments. So Gordon Peele, who was leading this work at TI, before this, everyone was working with germanium transistors, and then Gordon Peele and silicon transistors were considered this sort of non-feasible thing, which would probably not happen. It wasn't giving good results. It wasn't that good. So everyone thought that that's more like the academic stuff. Researchers are doing that. It's probably never going to come. But in 1954, in a conference or workshop somewhere, this Gordon Peele, what he did was he made a demonstration. As a presenter, he played a song on a transistor, a germanium transistor-based music player, and then what he did was he dunked it in hot oil, and obviously it broke, and the song stopped, and it wasn't working, which was obvious. But then he did the same with a silicon transistor-based system, and he dunked that in hot oil, and it kept on playing. And then he said that, and everyone was shocked, obviously. And then he said that silicon transistors are great. We have silicon transistors in mass production. And he was carrying one of them in his pocket. So it at that time, the silicon transistor looked like, it wasn't in the IC form. It was a single isolated device with 3 prongs and everything, which makes this, that is what is famous as the transistor thing. That is where we get the symbol for our transistor model and everything from, this black block with 3 prongs or 4 prongs. So that is what he was carrying in his pocket. And there was a mad stampede at that place. Everyone rushed to, read Gordon's paper on the subject. And there was a long-standing sort of corporate fight competition between Bell Labs and TI. TI was this new startup thing from Texas, and everyone was talking about it because they were making very bold claims and bold promotions, and they were primarily working with the US military for replacing vacuum tubes with silicon transistors. Bell Labs was, on the other hand, working with this telecom company. I think it was AT&T. I'm not sure, but I think it was AT&T. They were working with them, trying to develop these transistors for the whole telephone network and all of that. In the end, of course, TI gained a lot of success because of this, because of their aggressive marketing and everything. And it so happened that there were some delays in Bell Labs because of various things. And that delay actually pushed TI's product up, and they sort of became the king of the silicon devices. silicon transistors. The first MOSFET, the thing that we now call as MOSFET, the first time that came out was in 1959 from Bell Labs. And then we later in 1963, we went into CMOS logic. This was done at Fairchild. And of course, you know the rest of the history. We have been using this. We have been scaling the transistors constantly in the pursuit of less cost, less area, more speed, and better power consumption. And these are some of the milestones that I think are important in this whole scaling race. Around 90 nanometer node, this industry introduced the strained silicon to increase mobility. Around 65 nanometer node, we saw silicon dioxide thickness reduced to around 1.2 nanometers or so. Initially, it's interesting. Initially, the first transistors that were built in around 1960 or so, they were of the size of micrometers, like tens of micrometers. And for them, the oxide thickness was of the order of 300 nanometers. Then at around 65 nanometer node, they were scaling it. Obviously, if you keep reducing the oxide thickness, those of you who are familiar with, I'm sure all of you are, with the MOS structure, the gate actually keeps coming closer to the channel, and it has then more control because there's more field from the gate controlling the channel. So they reduced it to around 1.2 nanometers, which is very thin. If you reduce it further, there is a chance of leakage and breakdown coming into play. So around 45 nanometer node, they introduced the high K metal gate, which is right now it's hafnium dioxide. So these sort of materials are insulators with a very high permittivity. So what that does is keeping the same effective oxide thickness, I can actually have a thicker physical oxide thickness. So what that means is, because the physical oxide thickness is much thicker, there's less chance of a breakdown and leakage, while since the permittivity is high, it allows a lot of field to flow through it, and I do not lose out on the control that I get from a thin oxide film. Around 22 nanometers, we introduced the FinFET, which you all know and probably are working on. The next gen is nanosheets. These devices have been announced recently by Samsung, TSMC. Intel also came up with the nanosheet. They call it the ribbon fit recently. So it's more or less certain that we are going into the nanosheet direction, and it's obvious. It's the logical step from FinFETs. Okay, so that's sort of where we stand right now. Do you have any comments on this? Any questions? During this course, feel free to just unmute yourself and speak whenever you want to. There's no harm in stopping me or breaking me mid sentence. It's all okay.
So I have one question. So there is this one, right, to go to carbon nanotubes. So we are not no research is going on that. Just curious to know.
There's a lot of work going on carbon nanotubes. However, fabricating it for mass production is an issue, right? So on a research level, on a lab level, there have been a lot of publications based on carbon nanotubes, and some of them show promising result. But here's the key thing: for any transistor to come into the market and be mass produced and be used for the circuit IC development and all of that, it not only needs to be good as a concept or as a experimental transistor, it needs to look at and be better than the conventional silicon in multiple ways. One is, of course, the performance and everything needs to be better for the industry to invest in. The second thing is the cost associated with it. How much will it take to now fabricate this completely new type of transistor where a lot of the silicon based processes are not going to be helpful? So you have to develop new processes. That's a very cost intensive stuff. The fabs have to sort of revamp themselves to be fabricating carbon nanotubes, and this shift is a very costly affair. So to justify the shift, there needs to be enough performance gain so that we can say that, okay, the performance gain is so much that it is, I mean, completely stupid not switching to it. But that's not the case with carbon nanotubes. There is a performance gain in some areas, but then again, I mean, it's not enough at this moment, at least. Also, apart from the fabrication and all of that stuff, I there has to be thoughts about how you're going to build and integrate it into the whole circuit, the whole IC, whether the whole thing is now going to be silicon based with some carbon nanotube FETs, or whether you're going to do everything on carbon. If you're going to do everything on carbon, it's going to be very costly. So again, all of those concerns about how to integrate, how to fabricate, and all of that come into play. It's not like it can't be done, but the cost is too much, and it's not worth it from a profit point of view. This is working fine, right? When this stops working, or when we stop getting any performance gain for silicon, only then will people shift to something else. Other than that, they'll just keep milking silicon as long as they can, probably by adding a few things here and there, like they introduce the high K metal gate. They might introduce ferro materials in the gate stack sometime later, I don't know.
Right. Thank you. Because actually, I was just curious because from when I started as a career, right? So that time we were closer to like 4 nanometer, 5 nanometer, right? So from that time, the talk is going on that after nanometer, what is it? There is a question mark, right? So yeah. Thank you.
Yeah. So right now, what I understand, so when I think even 4 or 5 years back, there was this huge debate on what is going to happen next. And with this scaling, you guys know about the Moore's law, right? This Gordon Moore from Intel,
Yes.
he gave
Yes, sir.
about this scaling thing. Right. Yeah. So that is no longer valid. Okay, so there, for a long time now, we are out of this Moore scaling thing. So we are not able to keep up with that scaling rate because our devices have become so small now that scaling at that rate is no longer possible. You'll end up with, I mean, theoretically, if you calculate it out, you will end up with transistors having only a few atoms. We actually have already reached that stage. We are talking about gate lengths of the order of 12 nanometers or so, 10, 12 nanometers, which is what silicon is like 0.5 nanometer is approximately is the atomic spacing. So 10 nanometers is just 20 atoms. So now if you scale it further, you are not going to split the atom, right? So you are going to see a very discrete change if you go from 20 atoms to say 15 atoms, right? So it will be a very drastic thing, as opposed to when you are going from 100 nanometer to say, so from 90 nanometer to 65 nanometer, it wasn't that drastic. So now things have slowed down a lot. And we are trying to scale, and we are trying to figure out ways. So we have also changed our expectations. We are not actually expecting that much performance gain with each new transistor generation. So that is why we have now moved on from FinFET to nanosheets, where FinFETs, we had gate on all 3 sides. On nanosheets, we have gate on all 4 sides. What after that? You have gate everywhere now. So now probably nanosheets will continue for 1 or 2 technology nodes, where we keep improving the performance through design optimization and all of that stuff, and introducing some new design elements in the devices, and probably look at different materials now. Say if we can improve the gate stack somehow, if we can reduce the EOT further. EOT is the effective oxide thickness. So all of that is going on at the moment. I don't see a very stark shift from silicon to some other material immediately. At least from the road plan that all the fabs have sent out, at least for the next 5 to 8 years, I don't see a shift from silicon. But maybe after that. Okay.
Sir, actually, one small thing. Now at present, it's just based on this thing, like Intel, is promising for we are going to by 2025 we will reach almost like 1 nanometer. like 1.18 angstrom and so much news is there. So is it like we can go beyond this 1 nanometer possible, like in the silicon process? We can means
1 nanometer is what?
yeah, 1 nanometer of the gate length. Because now is like because Intel is almost like promising by 25, it's going to reach almost like 18 or like 1820 angstrom. So that is like a near to 1 nanometer. So
No, so here's the thing. Nobody is going to 1 nanometer gate length at the moment. So even the devices that so Intel has, okay, here's the interesting thing. Earlier, when we were talking about the 90 nanometer node, 65 nanometer node, the node number in a way correlated with the minimum feature length, which was also in most cases the gate length. However, now uh, because of the whole marketing thing, people have been naming their new technologies using a lower node number, but that does not imply any connection to the gate length anymore. So even Intel's latest devices are larger than 10-15 nanometer gate length. The nanosheet, the ribbon fit and all that they announced that they will bring by 2024, 2025, all of them will have a gate length of the order of 12 nanometers. So these node names are just names now. It has nothing to do with the actual design. It is all become a marketing thing. And if you see carefully, Intel's node names, they have gone from, they're now calling it Intel 7, Intel 4, and then this 18, which is the uh, some angstrom, if you're thinking. Yeah. It's not nanometer. They have removed the nanometer from the end. It's no longer 65 nanometer node, 22 nanometer node. No, it's just Intel 7. That's it. It's not 7 nanometer. Right, so the gate lengths are stuck of the order of 10 nanometers, 12 nanometers. No, we are not thinking of scaling them further down because we don't have that gate control yet.
yeah, thank you. Yeah. Okay.
Yeah, but to answer your question about less than 1 nanometer, theoretically it is possible. So there have been some experimental work, mostly in academia and academic research, where people have developed this was one of the papers that came out, I think 1 or 2 years back. I don't remember the year exactly, but what happened was, I think TSMC was also involved, but don't quote me on this. I'm not exactly sure. People demonstrated 1 nanometer gate length transistors or less than 1. So yeah, so you can check that paper out. There was a huge uproar and everyone was excited about it. If you just Google it, you'll find it probably.
Thank you.
Okay.
Sir, can we please talk about this high-K metal gate and what are the possible disadvantages of using high-K metal gate? Please?
Yeah. So high-K metal gate. So the reason I guess you all know the reason why it was brought in. Is around the 45 nanometer node. What happened was, so around the 65 nanometer node, we went to close to 1.2 nanometer silicon dioxide. After that, if we kept scaling the gate length of the transistor, we would have had to scale the oxide thickness as well, so that we maintain the same gate control. But if we scale the oxide thickness further, silicon dioxide would probably break down and there would be a huge amount of leakage current and all of that. So what people did was they introduced something called this high-K metal gate. The primary thing in that was this high-K material. Okay, so this gate stack, it usually has let's see if I can. So the normal MOSFET thing has above the semiconductor, it has oxide and then this gate, right? In the high-K thing, above the semiconductor, there's an interfacial layer of SiO2, and above that there is this high-K material, and then the gate. Okay, so what this does is, the high K material, something like HFO2, has a very high permittivity, which is the K, the relative permittivity, I think is of the order of 25 or so. I have to check, but it's of that order. So what that means is this material is very permeable to electric fields. Okay, so if I have to have a lot of electric fields from the gate reach the channel, then I can do away with a thicker high K material as compared to a silicon. So if I have a silicon and high K of the same thickness, not a lot of field will go into the channel through this. High K will allow a lot of field to go into the channel. So this thick high K is equivalent to a very thin SiO2. So using this, what we can achieve is this thing where you have a thick physical oxide thickness. So actually, if you measure, the oxide thickness will be like this thick. But as far as electrical characteristics are concerned, or as far as field penetration and all of that are concerned, to the electric field, this appears like a very thin barrier. So in effect, the electrical characteristics of the MOS device are maintained while keeping a thick oxide. Now, the benefit of keeping a thick oxide is the field across the oxide is dependent on this thickness somewhat. So the breakdown field, you need to apply a larger voltage, that is one. And also because of this thick oxide, there'll be less leakage and all of that coming into play. So that's good. So we are retaining the, gate control, but we are negating all the effects of thin oxide like leakages, right? So that is what we are doing. The problem with this high K material is the crystal structure of this material is not the same as that of silicon. So the atomic arrangement and all of that are not the same. So if I have silicon here and if I directly place HFO2 on top of it, this interface, this is going to be very bad. There will be a lot of interfacial states. There will be a lot of strain on this silicon and these materials. It's going to be a very bad interface and it's going to affect the device performance. Now, the way around is what people usually do is they have silicon, then they put SiO2. SiO2 and Si interface is very good. Okay, so this is say SiO2. So it's a very good interface. And then, is it restarting?
Yes, I think in 10 minutes.
Oops. Don't worry, I'll join from my other laptop.
It will take time in case it stops.
Okay, I'll just continue with this for the time being. Let's. Thank you. Right. Can you hear me now?
Yes, sir.
This is the volume. Yeah, sorry, can you hear me now?
Yes, sir.
Yes, sir.
Okay, excellent. Sorry, I'll continue where I left off. This thing. So this interface is we can put SiO2 on Si. So SiO2 Si interface is good, and then we can put a HFO2 on top of SiO2. So it is like a insulator interface. And anyway, the main interface of question and of concern is the SiO2 and Si interface, because that surface is where most of the charge conduction and everything will take place. So we want that interface to be as good as possible. So with that interfacial layer, we can actually solve that problem. Okay. So what we'll do now is we have a small quiz planned. Let me clarify. This quiz is not a graded quiz.
So
There will be
sorry to
no
interrupt.
marks. Yeah, go ahead.
We can't see your PPT. I'm not sure it's for me
Yeah,
or
yeah.
everyone.
We'll put that up. Yeah,
Okay,
I
okay.
just closed. Yeah, sorry. So during this, so what will happen is it's 9:42 now. This class will end at roughly at 10:30. So you have approximately 45 minutes of time. In these 45 minutes, we are going to share a small quiz with you, which will primarily be a multiple choice sort of thing. So you can just do that very fast. It's up to you. So this whole 45 minutes will be dedicated to you answering these set of questions. The purpose of this, let me clarify. This, first of all, will not go into any marking or your grades or anything like that. The purpose of this is to gauge where you stand with respect to this course and the stuff that I'm going to talk about. This will help me judge on which topics to pay most attention to and which topics I can actually skip and move ahead. Right? So it will probably help me make this course a bit more interesting and useful for you. Okay, we have our TAs with us. If Jyoti and Amit, you could share that link for the quiz. Yeah.
Hello. Yes, sir. We'll be sharing it, sir. We'll be sending the mails.
Shubhrata has already done it, so she had the email ready. So all of you must have received the link for, I think, a Google form. So take your time. You have the rest of the class today. We have another class at 2, from 2 to 3:30. So we'll start with the actual semiconductor physics and MOS device physics discussions from 2 o'clock. Also, I'm here till 10:30. So if you have any other questions or any other doubts, feel free to ask me. The TAs are also here. They will also answer all of your doubts and questions.
Has anyone received that link yet?
Yeah, please check your mail. We have sent from the Gmail account, mtechplsa@gmail.com.
No, no.
No, there's nothing so far.
I have got it actually.
Yeah. Okay, okay. One thing I will do, I will paste the link in the chat box only. Okay.
Okay, thanks.
Yeah, done. Please check. So filing it.
These are very tough questions.
अभी सर पी लीजिए ग्रीन टी या कुछ पिंक चाय या ग्रीन टी कभी नीचे जाके एक चाय और एक ग्रीन टी बोलो सतीश को बोल तो नीचे लिख लेना
Sir, for the question what we don't know the answer, can we leave them blank?
So your voice is too slow. Can you speak louder?
Yeah, so for the question for what we don't know the answer, can we leave them blank? No answer or something?
Yeah, yeah, please feel free to do that.
Okay.
But if you want to put a guess, you can also do that. Since it's not being graded, you have nothing to lose. So make your best guess.
Thank you. Excuse me, sir. Now, question 17, I have a doubt.
Okay, what's the doubt?
So the EC is conduction band energy or is the critical electric field? What exactly it was for question 17?
What I don't understand. You are asking about EC, right?
Yeah, EC is conduction band energy. Is it?
Right, right.
Okay. Okay.
Yeah, I have a request. Once you're done with the quiz, just type in the chat box here so that I know that you're done. So in case all of you are done before time, then we can do something else with that remaining time. Okay. Okay. I guess most of you will have completed the quiz by now.
Yes, sir.
Yeah. Is there anyone who's still working on it? No? Okay. Okay, so we'll end this class here. I'm guessing you'll have classes after this. So we'll prepare for that. We'll have the next class starting at 2, where we will get into the course and the theoretical discussions. One other thing is we have tutorials scheduled. So the tutorials will primarily be there to discuss the solution, different assignments, to clarify your doubts and queries. So this week's tutorial will basically discuss this quiz that you guys just did. So we'll just discuss all the answers to that quiz and how and what. And if you have any questions regarding that, this week we will also give you a very small assignment based on the lecture I'm going to take at 2 p.m. from 2 to 3:30, and you will need to submit it before Saturday, next Saturday, before the next class. Okay, and that's it. And we will discuss that the answers to that in the next week's tutorial. So the tutorial timing, we got the response from you, and thank you all for sharing your feedback regarding that. Based on several factors, we are thinking of doing this. So for the time being, we'll keep the tutorial on Saturdays in the evening at 6 p.m. It will be a 1-hour tutorial for this course only, 6 to 7. And we will do this for the next 1 or 2 weeks. And after that, you can give me your feedback whether you want to continue with it, whether you are facing problems and you want to change it. So it's sort of on a trial basis. Let's see if it works on Saturday evenings, so that all of us can have the Sunday free. If it doesn't, or if you're running into trouble, then we can shift it to some suitable time on Sunday. Is that okay?
Yes, sir.
Okay. Thank you everyone for joining. Thanks. I'll see you again in the afternoon.
Thank you.
Thank you.
Thank you, sir.